In this tutorial, we're going to compute the work along a path for a spatially varying force. So imagine that we're given a force of this form, where clearly the x component of that force, 2 newtons per square meter times x times y, depends upon the spatial positions x and y. That's all I mean by a spatially varying force. Now let's further imagine that this force is being applied to an object that is constrained to move along a path y equals 6 inverse meters times x squared between the x positions 0 and 2.0 meters. If we graph that path out, it looks something like this, where the object would start at the origin and move up and to the right until it reached x equals 2 meters and y equals 24 meters. That's the path we're interested in, and clearly from the form of the force will have a very different value at the origin, namely x and y equal to 0, than it will at x equals 2 meters, y equals 24 meters, and in fact it will change continuously between those 2 points. That's what makes this a challenging problem. One quick additional note. There's not an obvious relationship between this applied force and the path that we've specified, and that may worry some people, but actually it's okay. We don't know the net force acting on this object. We only know one of what could be many applied forces, and we can self-consistently compute the work associated with this force along that path without actually knowing the net force that led the object to go in that path in the first place. That established, we don't actually need the graph of the path anymore, so I'm going to erase that to make room for equations for work equals the integral of f dot dr and the position vector r equals xi hat plus yj hat. Let's start by writing out this integral. So the work equals the integral made definite from x equals 0 to x equals 2 meters of f dot dr. Now, given that both the force and the path are written in terms of x and y, our first task should be to rewrite dr into something involving either dx or dy. And we can do that if we look at the position vector and consider a differential element of r. Well, the I hat and j hat directions don't change, so the differential element of r just becomes dx I hat plus dy j hat. And we can substitute that expression in for dr and the dot product in our integral. So let's do that now. We'll also rewrite the force as fx I hat plus fy j hat. We'll substitute in the fx and fy components in just a minute after we take the dot product. So if we take the dot product, only the I hat dot I hat and j hat dot j hat terms survive, everything else goes to 0, so that leaves us with the work equals the integral of fx dx plus fy dy. And we can separate this into the sum of two integrals, namely the integral of fx dx plus the integral of fy dy, both from the limits x equals 0 to x equals 2 meters. We're going to do these integrals one at a time because each one is complicated in its own way. Let's label this one integral 1, and we'll start by solving that. The first step is to substitute in our expression for the x component of f, namely 2 newtons per square meter times x times y. So we do that, and now the problem with this integral is that it involves a y. Fortunately, the equation for the path equates y with 6 inverse meters times x squared, so we can just substitute in the equation for the path and get an integral that's entirely in terms of x, which is exactly what we want. Now we have a 1D integral, easy to solve. Let's combine and pull out those constants so that this integral becomes 12 newtons per cubic meter times the integral from x equals 0 to x equals 2 meters of x cubed dx. Well, the integral of x cubed is x to the 4th over 4. We'll plug in the two limits of integration, and we see that it becomes 12 newtons per cubic meter times 2 to the 4th over 4, or 48 newtons times meters. A newton times a meter is a joule, so that's a unit of energy. That tells us that the work associated with that first integral is 48 joules. Let's write that explicitly in the equation for the work so that we remember it. And our next goal is to solve the second integral. So we'll move this up and label this integral 2. So if we do that, the y component of the force is just minus 3 newtons. That part's easy. The problem now is that our limits of integration are specified in terms of x, but the differential element in our integral is in terms of y. We need to reconcile those two to solve the integral. First thing we'll do is pull out that constant minus 3 newtons out front. There are multiple ways to do this. My preferred strategy here is actually to rewrite dy in terms of dx, which we can do by calculating dy dx, namely the derivative of y with respect to x. How do we do that? Well, you'll see that this term, namely y, is just the equation of the path. So if we can just take the derivative of that with respect to x, that'll give us dy dx. Alright, let's do that. We pull out 6 inverse meters out front. We just have the derivative with respect to x of x squared. That'll just be 2 times x. So dy dx equals 12 inverse meters times x. That means that we can separate those differentials so that dy equals 12 inverse meters times x dx. And now we can substitute that expression in where we have dy in this integral. So let's do that. So that means integral 2 becomes negative 3 newtons times now the integral from x equals 0 to x equals 2 meters of 12 inverse meters times x dx. We can pull out the 12 inverse meters. Now we just have the integral of x dx, and that's relatively straightforward. That'll just be x squared over 2, evaluated at the limits of integration. We do that, simplify a little bit, and we find that the second integral is equal to negative 72 joules. So the total work associated with this force over that path is 48 joules minus 72 joules, which we can combine to get negative 24 joules. For the sign convention employed in this class, a negative work means that the object lost energy as a result of this force being applied over that path, and we know specifically now that it lost 24 joules.